We usually associate magnetic fields with stars and planets, but galaxies also have them. Magnetic fields play a major role in cosmic phenomena. In their time, they have worked hard to form the Sun and its surroundings, maintain the stability of galactic structures, influence cosmic rays, and control stunning processes in neutron stars and their surroundings. Cosmic magnetism rules at all levels of the organization of our universe. So how does magnetism arise, and where did it come from? In 1949, American astronomers William Hiltner and John Hall discovered the weak polarization of starlight in the Milky Way. In searching for an explanation for this phenomenon, they linked the polarization to the effect of the magnetic field on dust particles. A year later, scientists Leverett Davis and Jesse Greenstein estimated the magnitude of this field. Later, they found the same effect in the Andromeda Galaxy. This was the beginning of the study of cosmic magnetism. The origin of galactic magnetic fields is explained by two opposing concepts. Enrico Fermi put forward the hypothesis of relic magnetism, which arose shortly after the Big Bang. By the way, in 2006, Japanese astronomers supported this concept after conducting a series of studies. According to Fermi, galaxies captured and amplified these magnetic flows, resulting in the fields we observe today. Astrophysicist Eugene Parker explained galactic magnetism by the circular motion of the plasma in galaxies and their clusters. Later, this model of galactic dynamo was developed by other scientists. Although the theories of relic fields sometimes look very elegant, and some may even be correct, it is still necessary to accurately measure intergalactic magnetism, and this hasn't yet been accomplished. The fields inside galaxies and galactic clusters are another matter. Their occurrence is well described by the theory proposed 60 years ago by the German astrophysicist Ludwig Biermann. This mechanism is called the Biermann battery. Magnetic fields can also arise in other ways, for instance, in the rotation of plasma falling on a black hole. Nature has many ways to enhance this magnetization, for example, by compressing the cosmic plasma with shock waves. Such processes constantly occur in spiral galaxies, which ensures the stability of their internal magnetism. Galactic magnetic fields are also associated with the processes of star formation. It has long been known that stars arise as a result of the gravitational condensation of cold and relatively dense clouds of cosmic gas. Such clouds, each inch-3 of which contains from tens to millions of particles, sometimes extend for hundreds of light years. Particularly dense and vast clouds can give rise to hundreds or even thousands of stars. The processes of their birth appear to be completed rather quickly, within 10 to 15 million years at most. But the details of this process are not yet clear. Ordinary, baryonic, matter of outer space is a fully or partially ionized gas, which is a good conductor and therefore reliably holds magnetic fluxes so that in the interstellar environment the magnetic field lines almost never disappear completely. Such indicators are also typical for other spiral galaxies. In galaxies particularly rich in gas and, as a consequence, young stars, the magnetic field magnitude is larger, and in their central zones even larger. Elliptical galaxies are poor in gas, and therefore their magnetic fields are much weaker. However, as already mentioned, it is very difficult to measure the fields, so information about their magnetism is very fragmentary. Fields with induction also penetrate galaxy clusters, but magnetic fields haven't yet been found in the cosmic space separating such clusters. If they do exist, then they are extremely weak and most likely preserved from the infancy of our universe. Nowadays, almost all astrophysicists agree that a typical star emerges in 4 stages. First, the gas, or gas dust, cloud gets fragmented and clots of high-density matter are formed in it. Then, each of the clots is compressed by gravitational force, with gravitational collapse starting in the center of the clot and spreading to the periphery. This is how spherical protostars surrounded by rotating flat disks are formed. But the protostar won't become a luminary until it borrows a fair fraction of its matter from the disk. If this happens, this is the third stage, the protostar rapidly acquires additional mass, shrinks even more, and greatly heats up its own core. Eventually, its temperature reaches a few million degrees and the thermonuclear combustion of hydrogen begins. The protostar transforms into a star. In fact, galactic magnetic fields might play an important role in these processes. For the matter of the disk to fall on the protostar, it must lose some of its rotational momenta. This is precisely what the magnetic field contributes to. Already at the stage of disk formation, it bends the paths of protons, which collide with neutral molecules and also change their trajectories. This magnetic braking leads to internal friction, which reduces the rotational momentum. Later, when the disk is shaped, the rotation slows down due to another physical mechanism, magneto-rotational instability, which links the inner and outer belts of the disk and makes the former rotate slower and the latter faster. The life of main sequence stars ends with their transformation into compact objects, such as white dwarfs, neutron stars, or black holes. The latter has no magnetic field of their own, possessing only mass, angular momentum, and electric charge, while the others have magnetic fields that can reach fantastic values. A white dwarf forms after the gravitational collapse of a star that has exhausted its fuel reserves. For the vast majority of white dwarfs in the Milky Way, it is impossible to measure the magnetic field. But those that can be measured are highly magnetized, far more so than the Sun. They owe this to the collapse of an already magnetized parent star, which tightly compresses its magnetic field lines and thus increases the magnetic field by thousands of times. But the absolute record breakers for the magnetic part are neutron stars. Usually, their magnetic field value near the surface is 10 to the power of 12 Gauss. But sometimes the magnetic field magnitude is hundreds or thousands of times greater than this value. These stars are called magnetars. The magnetic fields of ordinary neutron stars, like those of white dwarfs, arise during the collapse of the parent star, but with immeasurably greater compression. The magnetic flux of such a star is closed inside a sphere with a radius of about 6 miles, instead of several thousand miles for a white dwarf. And the field in such compression is much stronger. But if you are seriously interested in astrophysics, then you probably have a question. Where does magnetism come from if neutrons have no electric charge? They have a magnetic moment, but it gives a completely negligible contribution to the magnetic field. The fact is that such stars are composed not only of neutrons. Their surface layers most likely consist of ordinary matter, and in the depths, there are charged particles, protons and electrons. They can participate in convective processes, generating currents in the interior of the star, which become the source of such a strong magnetic field. In the depths of a neutron star, originating from a strongly magnetized main sequence star and rotating at over 1,000 revolutions per second, a powerful dynamo is activated in the first moments of life, which accelerates the magnetic field magnitude to gigantic values. Together with the term magnetar, which was coined not so long ago, there is a theory according to which, in just a few seconds, the core of such a neutron star cools down so much that convection stops and the dynamo stops working. However, the super-strong magnetic field persists for a long time, because it is frozen in a superfluid environment, which has extremely high electrical conductivity. It is even possible that it is a superconductor. The magnetic field takes some of the kinetic energy from the star and gives it away in the form of radiation and particle emissions. Therefore, the rotation period of the magnetar grows rapidly, reaching a few seconds in just 10,000 years. This is exactly the angular velocity of almost all currently known magnetars. The magnetic power of neutron stars turns them into sources of continuous directed radio emission. The method of its generation is not yet known in detail, but the general explanation is as follows. The rotating magnetic field of a neutron star induces extremely strong electric fields, bouncing charged particles off its surface. These particles begin to move in spirals with a very dense winding, directed along the magnetic field lines. Such motion generates narrow beams of radio waves that escape into space along the magnetic axis of the neutron star. Since this axis doesn't coincide with the axis of rotation, each beam of radio waves outlines a conical surface in space. When the Earth crosses such a surface, the radio telescope receives radio pulses that follow each other at equal short intervals. Such sources are called radio pulsars. There are also more rare varieties of space illuminators, optical, X-ray, and gamma-ray pulsars. Magnetars work differently. These exotic stars irradiate the cosmos several times at a time in short but extremely powerful bursts of soft gamma rays and X-rays. The magnetar fields are so strong that they are unable to remain stable for long. Little by little they deform and cause strong stresses in the substance of the shell, localized in small areas. When the stress exceeds the strength limit of the crust, it bursts and breaks very rapidly, in about 1/10 of a second. The magnetic field in this place breaks out and spirals, creating the strongest perturbations of the magnetosphere. As a result, concentrated beams of high-energy photons that we register as bursts of soft gamma rays and X-rays are generated. As a rule, the first giant burst is followed by weaker ones, and the magnetar gradually shuts down. However, this exotic object deserves a separate video, since it is too mysterious and powerful. If you were interested, then give thanks to our channel. You can do it by giving a like to this video and writing a comment.